Hi everyone, on this next installment of the Internet Ecosystem and Evolution lecture series. And Previously we started we basically introduced this large-scale structure of the Internet. We defined the notion of what an autonomous system is, and then we started to discuss what we called the service model. The service model is something which describes the business relationships that can exist between two autonomous systems, and we use this service model as a basically main driver to build a mental model of what's going on in the internet between at the granularity of autonomous systems, and how the large-scale structure of the internet arises as the collection or the synthesis of all these individual AS to AS business connections that can happen out there. We started to discuss the transit service, which was the simplest type of service that can exist between two ASs, and we are going to just continue with describing the transit through this lecture. We give the definition of what we mean by the customer cone, and then we describe the way usually the transit provider usually uses to charge the customer for the transit service it provides. Then we jump to the next very important constituent of our service model. We're going to see that there is another very important AS-AS business relationship besides the transit relationship, and this we call the peering relationship, which we give the definition notation, and then we go into a couple of interesting details about the peering ecosystem of the internet. And at the end of this lecture, we are going to be in the position where we have enough understanding of this large-scale structure of the internet through our simple service model and through these two notions of AS-AS business relationships, the transit and the peering relationship, to actually build a very good mental model of the AS level hierarchy of the internet. We are going to just use this mental model to just create for ourselves a big picture of what's going on in the internet, and then we're going to discuss a couple of interesting facts about the evolution of this large-scale structure of the internet. So again, a little bit of a repetition from the previous lectures. Again, an autonomous system is a collection of a set of hosts and routers and networks that an organization owns and administers as a unit, and exposes a unified policy to the rest of the internet. And we now know that unified policy basically means that whenever traffic from, say, AS1 to AS2 is allowed to flow through AS3's network, then this usually pertains to all the hosts that are located in AS1 and all the hosts and routers that are located in AS1 and AS2, because these are basically handled by AS3 as so-called policy units. The service model was our actually help to reason about the types of physical connections that can be established between neighboring ASs. So this is basically the types of connections that together make up the topology of the internet at the AS level. So this was the first thing that we for which we used the service model to reason about the internet topology at the AS level. And the second important way we use the service model will be in the next lecture, and we start to discuss internet routing and the types of routes that arise on top of this internet. We just started to basically introduce this big idea that there is something which we call policy routing architecture, and we actually the fact whether AS2 actually allows the traffic of AS1 and AS3 to flow through its network is governed by its business and political and security interests, and these particular interests will be the ones that will actually just say block the flowing of traffic between AS1 and AS4 through the traffic through the network infrastructure of AS2. And now we can just by knowing that there is something which called the transit relationship, we now immediately know that this will be the case. So AS2 will allow traffic to flow through between AS1 and AS3 in its network whenever it has a transit relationship with all of these, with both of these ASs, because in that case AS2 will charge transit fee both for AS1 and AS3 to exchange that traffic. So it has a very, very a very definite economic interest and incentive to actually provide these sort of connectivity services to these ASCs. Now, the collection of all these different business and security interests is called policy routing. And we are the first very important AS level business relationship in our service model was a transit service, when there is a customer AS that contracts a service provider AS to deliver its egress traffic to any host connected to the internet, and to deliver all the ingress traffic from the rest of the internet back to the customer AS. And of course, this is basically just connectivity to the rest of the internet in a similar vein as we buy connectivity as individual internet subscribers from an internet service provider. The only difference here is that the actors that are actually exist in this transit service are now complete ASs with lots of hosts and routers in themselves, instead of individual subscribers and internet service providers. And of course, similarly to how we do at home, we're connecting our home network to the service provider network, where we actually charged by the provider for the service that it provides to us. The same stuff goes on in the transit service. The customer is charged by a traffic by the traffic rate it exchanges to the rest of the internet. So this basically boils down to paying a monthly fee to the transit AS. How that actually fee is paid will be one of the most important topics of this lecture. One very important aspect, or one very important observation that we made, was that whenever a transit provider actually provides internet access to a customer, in one way or another, it will need to announce the customer's prefix to the rest of the internet. Recall that this announcement actually means to the rest of the internet that please, if wherever there is any other AS on the internet, you can route the traffic that pertains to the customer prefix to the provider AS, because from that point the provider AS will make sure that the traffic will find its way to the customer's AS. From there, any host that is numbered from this particular prefix that is now assigned to the customer. Now either this announcement exists explicitly, and this was the case when the customer's address range is not aggregatable into the provider's address range, because in this particular case there will be a specific announcement that will be generated to the rest of the internet that will be specific to the customer's prefix. Or whenever we use provider aggregatable addressing, which means that the address range of the customer will be covered by the prefix of the provider. In that case, we don't need to announce this customer prefix separately, because the provider's announcement will cover the customer's address range. This brings us to a very interesting question, and this observation will give us the insight that we are going to use to reason about the size and the importance of ASs, or actually try to measure something which is so much subjective and subject to individual discussions, what we mean by the importance of an AS. This is something which is very difficult to reason about exactly, but the previous observation will give us a basis to just do that. Okay, so the importance of an AS is proportional to the number of customer ASs to which the AS actually provides transit service. So whenever there is an AS that provides transit to hundreds of customers, and through those direct customers, it also provides access to the customers, because it can very well happen that the customer sells the service that buys from us to other customers, then we kind of intuitively assume that that particular AS that service serves lots of customers with transit service must be somehow very important to the internet, and the customer count is essentially the number of ASs to which a particular AS provides transit service either directly or indirectly through other customers. Now, the problem is that the very number of these ASs might be a little bit vague in this sense, but because it weighs different customers differently, even though certain customers might be much larger than other customers. So a more characteristic metric might be the size of the address range that is announced by an AS into the interdomain routing system. We've seen that whenever there is a customer and there is a prefix range that is used by the customer, the size of the prefix range will be a good descriptor of the size of that particular AS, so the number of different IP hosts within that customer AS, and that particular address range will need to be announced by the transit provider to the rest of the internet. So this basically means that whenever there is a customer, the provider will cover that customer's prefix by an announcement. So if we just look at the size of the address range that is provided by that is announced by an AS into the interdomain routing system, then we get a very good estimate of the number of the individual IP addresses that are somehow directly or indirectly a customer of the transit AS. So the rest of this lecture series, whenever we talk about the importance or the size of a particular AS, we're going to mean by that the number of individual IP addresses or the number of equivalent /8s that is announced by an AS into the interdomain routing system. We're going to see in a lab a couple of occasions, a couple of labs later, the Internet Monitoring Lab, how to actually just identify all the prefixes that are announced by an AS into the interdomain routing system. This is something which is very simple to do, and most of the time this will be a good measure of the importance of an AS. So far so good. Let's jump to the next important topic here, and this is what we call the transit pricing model. The fact is that we've seen that the provider actually provides a fully fledged internet access to the customer in a transit service, and of course in return it charges the customer a monthly fee that covers the expenses of this internet provisioning service. Of course, this transit service and the parameters and the important clauses in this service is actually fixed by a formal contract between the customer and the provider, and this is called the service level agreement. So the SLA is the collective name of all the contractual parameters that are fixed between a customer and the provider in the transit service. Most of the time the SLA describes the parameters that describe the quality of the transit service provided by the provider AS. Most of the most important or one of the most important parameters is availability. So for instance, the transit provider can ensure or guarantee that the transit service will be available 99.99% of time to the customer, and if this is not the case, then there will be separate clauses in the SLA to cover whenever this availability requirement is not met by the service provided by the service provider. Other important parameters or quality of service parameters are the rate or the bandwidth, packet loss, delay variation, etc. Variation. These are all important aspects that might be fixed in the service level agreement. And there is one other important aspect that is also usually fixed in the service level agreement, and this is the way the actual actors, the customer and the provider, use to monitor the fulfillment of the service, the parameters, the service quality parameters that are fixed in the service level agreement. So the signers basically agree how and where they measure the quality of the service. Sometimes they can even call for third parties, with different enterprises which provide monitoring services to service providers, and whenever there is a dispute, the third party can decide whose assumption about dispute is cool. Now, in return, the other thing that is actually also covered by the service level agreement is the way the customer is charged for this service, and this is usually goes by a progressive pricing regime. The progressive pricing regime is applied with respect to the measured traffic rate on the provider customer AS link. So let's look into what we mean by this progressive pricing regime. What happens here is that so there is a very strong incentive for the service provider to actually enforce the customer to predict its own expected traffic rate to the best or to the most exact way possible. And this is because the service provider will need to provision all the resources, typically the bandwidth and the router capacity that is necessary to cover the service quality parameters that are fixed in the SLA for each of its customers. So it needs to do service provisioning and service dimensioning well ahead of time to actually prepare for to handle the traffic that it will receive from its customers, and that's why it will need to have a very good estimate on the expected traffic range, traffic rate of each of its customers. Now, how actually the progressive pricing regime that we've seen here is a very important way to actually force the customer into predicting its own expected traffic rate to the highest extent possible. So what happens here is the following. Here we have the important definition that we need to remember here is the commit. The commit is basically the customer's expected traffic rate for the next pricing period. So suppose that the customer sort of reports or indicates, so it actually the customer contracts at 10 megabit per second commit. This means that the customer expects its traffic to usually to remain below 10 megabit per second, and in this particular case, if this is the case, the customer will be charged $12 per each megabit per second it generates and consumes throughout this pricing period. But one very important aspect here is that whenever the customer traffic does not reach 10 megabit per second, then it will still be charged for as if its traffic reached 10 megabit per second. So there is an actual minimum price, which is 10 megabit per second times $16 per month per megabit per second, which is $120 per month. So again, whenever a customer makes a contract at a particular commit, that particular commit means that there is that whatever happens, even if it does not produce a single byte on this transit link, it will still cover the minimum price after that commit. Now, if the commit is 100 megabit per second, we immediately see that the price per megabit per second falls way below what we had in a smaller commit. So if the commit is higher, the price per unit is much lower. So this is basically a cheaper option for the customer to use this commit. But the problem is that whenever its traffic does not reach 100 megabit per second, it will still be charged for the minimum amount for this particular rate. So the commit is actually the minimum range, the minimum rate by which the customer will be priced. But the higher we go into the higher commit we choose, the smaller the actual price per unit. So the higher commit we choose, a customer chooses, the smaller relative price it will get from 1 megabit per second, and the variation is quite significant between 10 megabit per second and 100 gigabit per second commits. So wherever we generate lots of traffic, we pull very small price for each megabit per second. But of course, the problem is that whenever we take the commit of 100 gigabit per second, the minimum fee that we'll need to pay to the transit provider will be $7,000 a monthly fee, which is of course something which increases as the commit increases. So what this progressive pricing regime says is that the customer should find the commit that is sufficiently and necessarily large to cover its own traffic rate, but already large enough to actually get the smallest price per unit that it can have. Okay, so whenever the customer chooses the commit 10 megabit per second, it will get $12 per megabit per second unit price. This means that the customer pays 12 USD per megabit per second traffic unit, but whenever the customer, by any means, whatever happens, the $120 will be paid by the customer, even if the rate remains below 10 megabit per second, even if the customer does not produce a single packet on this connection. $120 will be charged by the transit provider. So the larger the commit, the smaller the price per unit, but the higher the minimum price. And this progressive pricing regime will force the customer to actually try to predict its expected traffic rate as closely as possible and choose the commit that is optimal and the smallest possible for itself. And this provides a way for the transit provider to actually be able to dimension its own service level agreements with its own providers. The other problem is that most of the time internet traffic varies on a wide scale, on an hourly, daily, and even on a weekly basis. So how to actually represent something which we call the expected traffic rate in such an environment where this particular traffic rate is subject to fluctuations from 1 terabit per second all the way to 3 terabit per second. So this is something which is highly variable, and we need to find a single measure to characterize this highly variable quantity that is the traffic rate of a customer. What we're going to use is that we are going to use the 95th percentile to characterize the traffic rate, and this is the usual rule that is used by providers to charge the customer. So wherever we need to measure the transit rate, here is what we are doing. We use the 95th percentile methodology, which means that first we sample the traffic rate on the customer provider ASAS link. So this is basically the link between the corresponding border routers, say every 5 minutes. So we basically give a reading of the traffic rate and we store that for a particular pricing period. At the end of the measuring period, we sort the measured samples in ascending order. Smallest sample comes first, and then progressively larger and larger traffic rates that we experienced at one of the 5 minute intervals during this measuring period. Still, we can clean up the data, so whenever there are erroneous samples that come from counter overflows or router reboots, which usually just zero out our counters and give unrealistic negative rate readings, these are usually just thrown away. And what remains is a collection of samples and increasing in ascending order. And then we take the 95th percentile of this sample set. So we choose the smallest sample that is already larger than or equal to the 95% of the samples. Okay, this is the simple 95th percentile rules. In other words, we say that the traffic rate that is measured by the provider in such a way that the 95th percentile will have this property that the customer's rate was below the 95th percentile in 95% of time. A couple of examples, there will be a lab about that also, but a couple of examples are in order here. Imagine that we have a sequence of 100 samples consisting of 99 readings of 1 megabit per second and one reading of 100 megabit per second. Okay, in this case we see that it is the 95th entry in this this list that has this property that 95% of the samples is below this particular value. Recall that the samples are in ascending order. This basically means that the customer will be priced for 1 single megabit per second traffic rate, even though there was just one period in this measuring period when there was a high burst. This 95th percentile measuring rule makes it possible for the customer to actually just drop these highly bursty measurements. But whenever the sequence is like the following, we have 94 samples of 1 and only 6 samples which are larger than that, say 15, 16, 16, 17, 21 and 40, we see that the 95th percentile is 50. So even though 94 percentile of the time the traffic was just 1 megabit per second, the 95th percentile is already 15 megabit per second. So this will be the traffic rate that will be charged by the service provider. How this happens? This is fairly simple. Suppose first we need to know the commit. So suppose that the customer chose the commit 10 megabit per second. We go back to our little table and we see that whenever the commit is 10 megabit per second, so we are here, then the price per unit is $12 per megabit per second. We just multiply it with the 95th percentile traffic rate to get $180 in total. Okay, so that's fairly simple. Just multiply the traffic rate with the price per unit and you get the eventual price. What happens when the customer chooses the 100 megabit per second commit? Naively, we would do the same. So we would just multiply the price per unit with the actual traffic rate to get something like $75 per month. But this would be wrong. And why this is wrong? Because 15 megabit per second, recall, the measured traffic rate does not reach the commit of the chosen by the customer. But whenever a customer chooses a particular commit, it basically makes a promise to the provider that whatever happens, it will pay the minimum price that goes with this particular commit, which is $500 per month. So even though we would get only $75, this will be the minimum price that will be charged by the service provider, and the customer will be charged by to $500. So that's the big idea in commit, and that's the big idea in this progressive pricing regime. That this is one of the ways the provider actually pushes and stresses the customer to try to predict its own traffic rate as closely as possible.